Hello everyone, welcome to the Theoretical Computer Science at Jagiellonian seminar. Today our guest is Torsten Mütze from the University of Warwick and Charles University in Prague. Torsten got his PhD in 2011 at ETH Zurich, and since then he worked in supercomputing systems Zurich, then again at ETH, then Georgia Tech, TU Berlin, and now in Warwick and Prague. He is well known for his work on combinatorial generation and Hamilton cycles in highly symmetric graphs, in particular for the solution to the middle levels conjecture. I also had the pleasure to participate in part of this research. It was about Hamilton cycles in Kneser graphs. And today, Torsten is going to tell us about efficient generation of elimination trees and Hamilton paths on graph associahedra, which is a work accepted to SODA 2022.
Thank you very much, Bartek. Thank you also, Piotrek, for the invitation to this seminar. Yes, what I present today is joint work with Jean Cardinal from Brussels and Arturo Merino, my student from TU Berlin. So let me start very broadly. In computer science and discrete mathematics, we often encounter different classes of combinatorial objects. So for instance, we may encounter the class of all binary trees on a certain number of nodes, or maybe we care about all the permutations on some ground set, or we care about all the binary strings of a certain length. Or to mention a more exotic example, maybe we may look at the graph and we may look at the set of all of its spanning trees. Yeah, so these are typical classes of combinatorial objects, and this list could be continued, so you can imagine your favorite class of objects here. And then there's a set of recurring fundamental tasks that we want to do with these objects. So for example, we may want to count the objects, so we want to know how many objects are in this class. Or oftentimes we want to sample uniformly at random one of these objects. Another important task is, of course, optimization. So we want to find the best object from the class according to some objective function. In this talk, I will focus on a fourth task, so not the first three, but on another task, and this is exhaustive generation, which means we want to exhaustively generate all the objects from the class, each object exactly once. And this topic is covered extensively, for example, in Knuth's book, The Art of Computer Programming. In the most recent volume, there's a large part devoted to this topic. So the goal is to have an algorithm that generates all the objects of a combinatorial class efficiently, every object exactly once. And ultimately, we aim for an efficient algorithm, and the ultimate goal will be that each new object is generated in constant time. So when going from one object to the next, we only spend constant time, and this is somehow the best we can hope for. This is not maybe always possible, but this is somehow the ultimate goal that we aim for. And if we aim for this goal, then it makes sense to generate the objects in such a way that when going from one object to the next, we only change them a little bit. We only apply a local change, because then we can hope to find such an efficient algorithm. Whereas if the change is very complex, then it may take a lot of time to compute this change. And such a minimum change ordering of objects is often referred to as a gray code. So here are some examples for such classical gray code results. So for example, it's known that you can generate all binary trees on a certain number of nodes, and in each step you only apply a single tree rotation. Yeah, this is one classical result. Another classical result is the Steinhaus-Johnson-Trotter algorithm, which allows you to generate all permutations of a certain ground set, and in each step you only apply one adjacent transposition, so you transpose two neighboring elements in the permutation. Another classical result is, of course, the binary reflected gray code, which allows you to generate all binary strings of a certain length, and in each step you just flip a single bit. And also a very old result is that you can generate all the spanning trees of a graph by edge exchanges. So in each step, you only remove one edge from the spanning tree and instead you put in another one. So these are examples of gray codes for these 4 classes of objects that I mentioned in the beginning. And these gray codes, they lead naturally to the notion of a flip graph. So what is a flip graph? In a flip graph, the vertices of the flip graph are the combinatorial objects that we want to generate. And the edges of the flip graph, they connect pairs of objects that differ in a small change. So they capture the change operations that we allow applying when going to the next object. So here's such an example of a typical flip graph. This is the flip graph of binary trees of 4 nodes under tree rotations. And this is how it looks like. And this is the flip graph of permutations of length 4 under adjacent transpositions. And this is the flip graph of binary strings of length 4 under flipping a single bit. And the last example is, so this is the flip graph of spanning trees of K4 under edge exchanges. So the objects are the spanning trees and the edges, they capture changing one edge in the spanning tree. And these flip graphs that you get in this, so this is a huge variety of flip graphs. Yeah, so you can choose your favorite object and your favorite change operation, and based on this you get a flip graph. And there's many different ways how you can do this, and therefore many different flip graphs you can get. And in many cases you get graphs that are interesting in the sense that this is not just some random graph, but they have a lot of structure. So often they can be realized as polytopes or equipped with some poset structure. So for example, in these 4 cases, this graph here, this is the well-known associahedron. This can be realized as a polytope, and it can also be equipped with a lattice structure, and this is the Tamari lattice. On the right-hand side over here, you see the permutahedron, and the corresponding poset or lattice even is the weak order, the weak Brouwer order. And on the bottom left, you see the well-known hypercube or the Boolean lattice. And on the bottom right, you see the base polytope. I'm not aware of a corresponding poset in this 4th case here, but the base polytope is the corresponding polytope. And of course, this task of exhaustively generating the objects now in those flip graphs corresponds to traversing a Hamilton path or cycle in this graph. And in these 4 cases, there is such a Hamilton cycle. And the difference between path and cycle is only whether, for the generation problem, you don't care about the cycle, right? You just want to see every guy exactly once. And the cycle is somehow this extra feature that, oh, by the way, you can also go back from the last object to the first and make it a proper cycle. This is somehow an additional nice feature that maybe you sometimes want. If you just care about efficient generation, this is irrelevant because you don't want to go back to the first one. Okay. Moreover, these flip graphs, not only do they have a lot of structure, but often they are highly symmetric. In some cases, even vertex transitive or regular graphs. So for example, the permutahedron is vertex transitive. The hypercube is vertex transitive. The associahedron is only regular. It's not vertex transitive. So you get nice graphs. And there's a famous conjecture due to Lovaas, which connects this Hamilton cycle problem in flip graphs to this vertex transitive property. Namely, his conjecture says that every vertex transitive graph has a Hamilton path. And this is, of course, very much open, this conjecture. But it can serve as a motivation as to why, another motivation as to why we care about finding Hamilton paths and cycles in these flip graphs. In this work, the class of combinatorial objects that we want to look at are elimination trees of a graph G. So let me first define for you what an elimination tree is. So we start with a connected graph G. And what we do is we remove vertices of G, one after the other. And we put those vertices into a tree. So we start by picking a vertex V of G that will become the root of our tree. So this is a rooted tree. And then we remove the vertex V. This creates the graph G minus V, so a smaller graph. And then we recursively apply this removal process on the remaining graph, and those will become the subtrees of V in the rooted tree. So let me show you an example. So let's say we look at this graph G here with 5 nodes. And on the right-hand side, I want to construct one particular elimination tree for this graph G. So let's say we pick the first vertex 2. Let's say that this will become the root of our tree. So the first vertex we remove is this vertex 2. So we remove it from the graph. It will become the root in our tree T. And removing this vertex creates 2 connected components, the red one and the blue one, meaning that in the tree, this root vertex will have 2 children. One I get for the red graph and one I get for the blue graph. Okay, so now I recurse. So let's say I first recurse into this red part. So and I may choose this vertex 3 to be removed next. So this will become the next vertex in my tree. And then when I remove 3 from the triangle, a connected graph remains on those 3 vertices, namely a single edge. So now I may continue remove 1 and then I remove 4, and now those vertices are gone, and the only thing is left is this right subtree, and there's only 1 vertex, and this is 5. Okay, so this is one particular elimination tree for this graph G. And of course, there's many different elimination trees corresponding to different orders of removing the vertices from the graph. And now I look at all the possible elimination trees for the given graph. So this is a set of objects, and this is the set of objects I want to generate now. There's a slight generalization of this notion. The definition of elimination tree I gave is for a connected graph G. If your graph is not connected, then you get an elimination forest, and this you get by doing this elimination tree for each connected component. So an elimination forest is a set of elimination trees, and one for each connected component. Okay, are there any questions about the definition so far? Doesn't seem to be the case. Yeah, please feel free to interrupt and ask questions. So let me say a few more words about the correspondence between this elimination tree and this process of removing vertices. So the way that we should think about this elimination tree, we should think about it as a process in which I remove vertices, and this order in which I remove the vertices, this is what we call an elimination ordering. So this is nothing else than a permutation. So this permutation 2, 3, 1, 4, 5 is one elimination ordering in which I remove the vertices. So I first remove 2, then I may remove 3, first 2, then 3, then 1, then 4, then 5. This is one particular elimination ordering that gives this elimination tree. However, this is not a one-to-one correspondence. This is another elimination ordering that gives the same tree, simply because the ordering between 5 and 4 doesn't matter, because they are here in separate branches of the tree. And this is another elimination ordering that gives rise to the same elimination tree, and this is a fourth one. These are actually all the ones I think that correspond to this tree. So this is a set of elimination orderings that all correspond to the same tree. And this correspondence can be made precise by the following statement. This set of permutations, the set of elimination orderings that correspond to the tree, this is just the linear extensions of the tree poset. Yeah. So all, if you turn it upside down, so you should imagine that the root is the guy you remove first, and then you remove from top to bottom. So this set of permutations here is the set of all linear extensions of this tree poset, if we imagine that this is the minimum and the maximum goes downward. So I have the tree poset turned upside down. Okay, this is the formal correspondence. And there's a few related notions to this notion of elimination trees that I want to mention on this slide. They will not appear anymore later in the talk, but I still want to mention them because some people may know them and may be able to connect in this way to what they know. So one, of course, very heavily studied notion is the notion of tree depth of a graph. And this you can define simply as the minimum height of an elimination tree, minimized over all possible elimination trees of the graph. Another notion that you will often find is the notion of a vertex ranking. So this is a labeling of the vertices with integers 1 up to k, such that on any path between two vertices with the same label, there is a vertex with a larger label. So in this example, let's say we look at the same graph and we label with 1 to 4. There are two vertices with the same label 2 here. And this is a valid vertex ranking because on this path from there's only one path between them, and this one path between them has a vertex with a larger label, namely this label 3 here. And this you check for any two vertices with the same label and for any path between them, and then this is a vertex ranking. Also, there's the notion of centered coloring. So this is the coloring of the vertices with C colors, such that in every connected subgraph, some color appears exactly once. And you can check that this coloring here also satisfies this. And all these notions are, of course, related. Namely, the minimum k for which there is a vertex ranking equals the minimum c for which there is a centered coloring, and this is equal to the tree depth of a graph. Okay, as I said, these words, tree depth, vertex ranking, and centered coloring, they will not appear anymore in the rest of the talk. I will only talk about these elimination trees, but there is this relation to these notions. Okay, so what I want to look at next, you may think that why should I care about the set of elimination trees? This sounds like a very obscure family of objects. Why should I care about generating precisely those guys? And the reason is that these elimination trees actually correspond to many different combinatorial objects that people have studied independently. If you choose this underlying graph G to be a specific family of graphs. So for example, if you choose for this graph G, the family of complete graphs, then what are the elimination trees? The elimination tree of a complete graph is just a path, because whenever you remove a vertex, what remains is still connected and is still a complete graph. So every vertex has just one descendant in the elimination tree, and therefore you get a path. And this path, of course, can be interpreted as a permutation. Yeah, so it's just the linear extension of this path is just one permutation. So there's a one-to-one correspondence between elimination trees of the complete graph and permutations. So when I say that I want to generate elimination trees, then this in particular means that I can generate permutations. Let's look at another example. If I choose for this graph G a path labeled 1 up to n, then what are the elimination trees of paths? If you remove a vertex from a path, you always have a left subpath left and a right subpath left. So this means that every node has two descendants unless there's no path left. So this means the elimination trees, they are binary trees. So the elimination trees of paths are binary trees. And there's one little subtlety here. So a binary tree has always a notion of a left subtree and a right subtree, and you can distinguish them. In an elimination tree, there's no ordering among the children. So the children of a tree are not ordered. But in this case, this ordering is induced by the size of the labels. So if I remove a vertex, then all the smaller labels, those are what I call the left subtree, and all the bigger labels, they are in what I then can consider the right subtree. So this, what left and right is induced by the size of the labels, by the smaller and larger labels. Okay, so elimination trees of paths are binary trees. And when I say I want to generate elimination trees, I implicitly say I want to generate binary trees, which is an interesting task maybe. What about stars? So if the graph G is a star, and now for some reason I label the center 0 because this plays a special role, and I label the leaves 1 up to n, then what are the elimination trees? As long as you keep removing leaves, you only have one descendant. But once you remove the center node, once you remove the node 0, then immediately everything is a descendant of 0. So you get a broom. So the handle of the broom, these are some leaves, and then once you remove the center, all the rest is the children of the 0 vertex. And what is the combinatorial object behind it? Or what is the combinatorial interpretation of this? Well, this is what we can call a partial permutation. So basically, you look at the labels that you see in the handle of the broom, and you read it from top to bottom. So you read it 5, 6, 3, 1 in this case. And you forget about everything that you see below here. So a partial permutation is a total ordering of a subset of the leaves. Yeah, and all elimination trees are in one-to-one correspondence with all the partial permutations that you get. Okay, so this is again another interesting family that people may be interested to generate, and it's a special case of elimination trees. Now let's look at the disconnected graph. If G is a bunch of matching edges, so now G is disconnected, it's a bunch of edges, meaning that the elimination trees are now elimination forests, right? Because now I have a disconnected graph. Well, the elimination forests, they are also one-edge trees, one for each matching edge. And the only difference in each elimination tree is whether there's only two choices, which of these end vertices is the root and which is the leaf. And this means that I can interpret such an elimination forest as a binary string, right? I can just say, if the smaller node is the root, I put a 0, and if the bigger node is the root, I put a 1. And this is a one-to-one correspondence. So the elimination forests of matchings are in bijective correspondence to binary strings. So that's another interesting family, generating binary strings. Okay, now I talked about what we want to generate. So we want to generate elimination trees because they capture many interesting combinatorial objects. Now I need to define what is the operation that I want to use when going from one elimination tree to the next one. It should be this gray code type operation. It should be a minimum change operation, ideally. And the operation I will use is a tree rotation. And what is a tree rotation on an elimination tree? So suppose you have a graph G with and some elimination tree T, where two nodes I and J, they form an edge in the elimination tree, where I is the parent of J. So meaning that I was removed before J was removed. And an elimination tree rotation of this edge ij in the elimination tree now just corresponds to swapping the order in which you remove I and J. So you keep the removal order of all nodes the same, except you change the order of I and J. So instead of first removing I and then J, you first remove J and then I. This gives another elimination tree, and this is two trees obtained in this way. We say that they differ in a tree rotation. And this leads to some of these subtrees changing their parents. Specifically, what is a child of I remains a child of I, and what is a child of J here remains a child of J here. But some of these children here, these C and D, they change their parents. So here the parent is J, and over here the parent is I. But this is just a consequence of the definition. And we refer to this tree rotation by the edge that we rotate. So we call it a tree rotation of the edge ij. some of the subtrees change parent, namely those subtrees which in the graph are somehow between I and j in the graph. This notion of tree rotation generalizes the classical notion of tree rotation in binary trees, which you maybe know from any data structures class, where you've seen pictures that look like this. So in the classical binary tree rotation, you also have this edge, this red edge that is rotated, and precisely one subtree changes parent, namely this subtree B, which here is attached to this node, which would be J, and here after the rotation it's attached to I, whereas A keeps its parent and C keeps its parent. So in binary tree rotation, precisely one parent changes, one subtree changes parent, and in our case it can be more than one. And the interesting thing is that this notion of tree rotation corresponds to nice changes on those examples of objects that I mentioned before. So for example, this for permutations. So permutations I got by looking at G, the complete graph. The elimination trees, they were paths. And a tree rotation now just swaps the order of two nodes on this path, and this corresponds just to an adjacent transposition. Yeah, so this tree rotation generalizes adjacent transposition for permutations. Let's look, I already said that for binary trees, it corresponds to a nice classical binary tree rotation, so this is clear. Let's look at binary strings. So binary strings I got when I take, as the graph G, when I take isolated edges. The elimination forests are one edge trees, and the tree rotation now just swaps around one of these edges. Yeah, this just corresponds to flipping a single bit. So this is a generalization of flipping a single bit in binary strings. So all these special cases, or this general notion of tree rotation corresponds to nice local change operations in all those applications. So this is why this justifies some of this choice for choosing tree rotation as our operation. There's another justification, namely coming from polytope theory. There is a corresponding polytope which you can define for these elimination trees. And this is the graph associahedron. So for any underlying graph G, you can define a polytope, the graph associahedron A of G, whose vertices correspond to the elimination trees and whose edges correspond to tree rotations. So this is not really a definition of the polytope, nor is it a realization what I say here. This is just a combinatorial description. But there are geometric realizations and description of all the phases of all dimensions of these polytopes given in those papers. But what we care about is only the skeleton. So we only care about the vertices, which are the elimination trees, and the edges, which are the tree rotations. So this is all we need to know about this graph associahedron to continue following what I'm going to say. But there are also all these other aspects about these polytopes, like geometric realizations and so on, which I don't talk about. I will show you some pictures later. For special graphs G, this graph associahedron is also gives some nice special cases. So for instance, if G is a path, you get the standard associahedron. If G is a complete graph, you get the permutahedron. If G is a star, you get the so-called stellohedron. If G is a matching, you get the hypercube. If G is a cycle, you get the cyclohedron. So all these polytopes have been studied in their own right, and they are generalized by this notion of graph associahedra for any graph G. So here are some examples. Here, if your graph G is a path, you get the associahedron. Here you see a concrete realization in 3D projected to 2D. At the vertices, you see the elimination trees here in black, and you see the corresponding binary trees in blue. So this is precisely this flip graph of binary trees under tree rotations. If you take the permutahedron, if you take the complete graph, you get the permutahedron. Here you see the corresponding elimination trees, and in black, and you see in blue the corresponding permutations. Here you see the stellohedron for a star. You see the corresponding elimination trees in black, and in blue, these are these partial permutations which you get by reading off the labels on the handles of the broom and ignoring all the other labels. One important result about these graph associahedra that is relevant for us is the question of Hamiltonicity. There's an important result proved by Manville and Pilot that for any underlying graph G with at least two edges, this graph associahedron has a Hamilton cycle. Yeah, so they already constructed one particular Hamilton cycle. However, so this is a constructive proof. However, it's rather complicated. It spans many pages. And moreover, it's not clear whether it leads to an efficient algorithm to traverse this cycle. And by efficient, we mean a local algorithm that only basically stores the current elimination tree and knows which tree rotation to perform to move to the next one without storing all exponentially many elimination trees at once. Yeah? So such an efficient algorithm you don't get from this proof, or it's at least not clear how to get it. And this is somehow the starting point of our work. So the main contribution of our work is a simple greedy algorithm that can be made efficient to generate the elimination trees of a graph, at least for not for all graphs, but for a reasonable subset of graphs. And in order to describe this greedy algorithm, we want to have a very short encoding of tree rotations. So before I told you that we encode a tree rotation by the two endpoints. So we say rotate the edge with endpoints I, j in the elimination tree. And now we want to condense this a little bit more by as follows. So if this edge is ij, we look at the larger of the end vertices. In this case, let's say it's j. And then we describe this operation by only the movement of the vertex j. So this tree rotation of ij, we describe by saying that j moves up, and we denote it by this j up arrow. Yeah, so if I say j up arrow, then what I mean is look at the parent of j, and if it's smaller, do this tree rotation ij. And the converse would be j moves down, and this is then denoted by j down arrow. Okay, so what are so when I want to apply this operation, j moves up, what is the condition when this works? This is applicable if this is always applicable unless j is the root. If j is already root, I cannot rotate it up. And also the parent of j should be smaller. If the parent of j is not smaller, then this doesn't satisfy this condition. So then I cannot apply this j up operation. For this j down operation, there's a more severe potential problem. If I say j down, then there may be an ambiguity. There may be several smaller children of j, and then each of them would qualify for a tree rotation. So then if I just say j down, then it's not clear with which one I should rotate. Yeah. So if I see this tree and I say 7 move down, then, well, there's 2 smaller children, and then I don't know, should I rotate 7, 4 or should I rotate 7, 1? So these operations have to be treated with care. Yeah, sometimes they don't apply, and sometimes they are ambiguous. So yes, it's not always clear whether I can apply them. Okay, so now I will present in a pseudocode form this basic greedy algorithm that we want to use to generate the elimination trees. So the first thing is we need to initialize our algorithm. We need to say what is the elimination, and this is now immediately stated in full generality for elimination forests. So even if G is disconnected, this can work. So I initialize the algorithm with one particular elimination forest. This is not yet specified which one this will be. I will state a theorem later where we say which should be the initialization one. So suppose we initialized with one particular elimination forest. Now I need to tell you this greedy rule, how we move to the next one. Yeah, and this is a greedy rule. So the greedy rule will apply one tree rotation to generate the next tree. And the rule is as follows. You have already visited some elimination trees before, and you want to generate a new one. And what you try to do is you try to perform an up or down rotation of the largest possible vertex so that you get a new tree. New meaning something that you haven't visited before. And this you do by looking at the current elimination forest. So in the current elimination forest, you try up or down rotating the largest possible vertex so that you get something new. And there's two ways how this can go wrong. It can happen that no such tree rotation exists, then you are stuck. Or it can be that there's multiple possible rotations. So for example, the largest possible vertex may have several smaller children, and then you don't know with which one you should rotate because the algorithm doesn't break ties, at least in the way it's stated, it doesn't break ties. And then there's ambiguity, and in those cases, we decide that the algorithm should terminate. Okay. So one important thing to note here, this is just the conceptual description of the algorithm. This is not yet the implementation. In particular, this is not an efficient algorithm. This is just the conceptual description, and later I will talk about how to make it efficient. So in order to understand this greedy behavior, let's go through an example. Let's say we start, we consider this graph G, so the star with 4 vertices, and we want to run this algorithm R. And let's say we choose our initial elimination tree to be this one on the left. So the 1 is the root and 2, 3, 4 are the children. Now, what does it mean to apply this greedy rule? The greedy rule now looks at this elimination tree and tries to rotate the largest possible vertex. So it tries to rotate 4 first. This is the largest one. And well, what can we do with this 4? We cannot rotate it down because it is already a leaf, but we can rotate it up. So if we rotate 4 up, we get the following elimination forest. And this is a new one. It hasn't been visited before because we just had one elimination tree. So it's one successful step of this greedy algorithm. Okay, now we have generated the second elimination tree. Now again, we apply the greedy rule. Again, we try rotating the largest possible vertex. It's 4. Can we rotate the 4 down? Yes, we can rotate it down, but then we get the first tree again. So this is not a new tree. So rotating 4 down doesn't work. What is the next largest possible one? Well, we could try to do something to the 3. And we cannot rotate it down because it's a leaf, but we can rotate it up. So this is what we do. We rotate 3 up, and we get this elimination tree. And in this one, again, we try first changing the largest one. This is the 4. We cannot rotate it up, but we can rotate it down. So this is what we do. We do 4 down. And again, we can do 4 down. And then we arrive at this one. Now we cannot do 4 down anymore. And we also, because it's a leaf, and we cannot do 4 up because this gives something we have seen already. Can we do something with 3? Can we do 3 down? No, if we do 3 down, we get the first tree. This we have seen already. So we cannot do 3 down. So we have to do something with a 2. And this is what we do. We do 2 up. And in this way, it continues. So let me not go through all the steps, but this is somehow the idea. I hope the example clarifies somehow what happens. So you have somehow this priority ordering of vertices, and you always try to do something to the largest possible vertex, and if it doesn't work, you try to doing something to the second largest, and only if it doesn't work, you try to do something to the third largest, and so on.
It doesn't matter if you go first up or down when you have a choice?
That's a good question. This is one of these ambiguity cases. So the algorithm the algorithm doesn't, like, the way that the algorithm is stated is it only works if this is a non-ambiguous case, and it would give up if there was an ambiguity. So if you encounter a step where some node where the largest possible guy can go up and go down, and both are new trees, then the algorithm, the way it's stated, would give up, yeah, because it's an ambiguous situation. Of course, you could define some tie breaking and let's say prefer going up over going down. Yeah, this would be a different algorithm. In the way that the algorithm is stated now, this is an ambiguous situation, and we would give up immediately and the algorithm would terminate. Yeah, that's a good question. Actually, I think I have such an example now. Let's do the same algorithm for the 4 cycle, let's say. And for some reason, let's say we start with this elimination tree. And again, we start messing around with the 4. 4 goes up, 4 goes up, 4 goes up. Let's not go through all the steps. At some point, so there's some intermediate ones, which I omit here. At some point, we come to this tree. And now we come to such a case that Piotrek mentioned. In this case, we can change the 4. We can move it up. This would give this tree. And we can move it down. This would give this tree. And both of them are new. So none of them appears already in our list. And then the algorithm gives up. Yeah, so the algorithm terminates because we are in this ambiguous situation. We could maybe break ties, but this particular algorithm gives up and then stops. And in this case, it's a failure, yeah, because the algorithm stops at a time where it has not yet generated all the elimination trees. Oh, by the way, in the previous example, the list that was generated was complete, so all the elimination trees were there. Whereas in this example, the algorithm stops before seeing all the elimination trees. And now, of course, we want to understand what are sufficient conditions that make the algorithm work. So what conditions do I need to impose on my graph G and on the first elimination tree so that this algorithm goes through without stopping prematurely, without generating everything exactly once. And this is captured in the following theorem. So the theorem is that if your graph is caudal and in perfect elimination order, then the algorithm will succeed. It will visit every elimination tree of G exactly once. And what about the initialization? If you initialize it with the elimination forest that you get by removing the vertices in increasing order. Yeah, so this caudal graph has a perfect elimination order. So the vertices, they have names 1 up to n, and they are corresponding to a perfect elimination order. I will give the definition in a moment. And if you remove them in this order, then this is the initial elimination forest that you should start with, and then the algorithm succeeds. Okay, there's a lot of definitions here, so let's go through them. Caudal graphs, this is probably familiar to some of you. Graph is caudal if every induced cycle has length 3, so no induced cycles of bigger length. This includes many interesting families, such as stars, paths, complete graphs, K-trees, interval graphs, and split graphs. So this in particular includes many of these special cases that I mentioned before. I mentioned complete graphs, which give you permutations. I mentioned paths, which give you binary trees. I mentioned stars, which give you partial permutations. It doesn't include cycles. Yeah? So cycles of arbitrary length, they are not caudal graphs. They are not captured by our theorem. And you saw already that the 4 cycle failed. Yeah, the 4 cycle is the smallest example where the algorithm fails, so it cannot be captured by this theorem because cycles of arbitrary length are not caudal graphs. What about this definition of perfect elimination ordering? So perfect elimination ordering means that you can sort linearly order the vertices of the graph with 1 up to n, and then if you look at the vertex J, you look at all the neighbors with smaller labels, then you want that these neighbors induce a clique. Yeah, so if I have this linear order, I look at the vertex J, I look at all the neighbors that have smaller labels, then they must induce a clique. And if this is true for every J, then this is a perfect elimination order. And that's a well-known theorem, a very old one. very well-known characterization of caudality, that the graph is caudal if and only if it admits such a perfect elimination ordering. Okay, so this is basically the definitions that should allow you to understand this theorem. Yeah, so if you have any caudal graph G, then it has a perfect elimination ordering. If you label the vertices in this perfect elimination ordering and then you run our algorithm, then it will succeed. Okay, so what are the consequences of this theorem? So first of all, we get a short proof that the graph associahedron has a Hamilton path if the underlying graph G is caudal. If it's caudal, we can run our algorithm. It produces this ordering of elimination trees by tree rotations, and this corresponds to Hamilton path on the graph associahedron. This Hamilton path, in some cases, it happens to be a cycle. Yeah, in some lucky cases, I will talk about this later. In general, it's just a path. And moreover, this theorem generalizes several well-known gray codes, in particular the Steinhaus-Johnson-Trotter algorithm, when G is the complete graph, the binary reflected gray code for binary strings, if G is a matching, and this gray code for binary trees that I mentioned in the beginning, gray code for binary trees by tree rotations. This is also a special case of this more general result. This is also, this is another remark. So the theorem is a sufficient condition. It says if the graph is caudal and in perfect elimination ordering, then the algorithm works. The converse is also true. This is not part of the theorem. This is another statement or another result. Namely, if the graph is not in perfect elimination ordering, then we can prove that the algorithm fails. So it gets stuck because of ambiguity. This is what we saw for the 4 cycle. The 4 cycle was not in perfect elimination ordering because it's not a caudal graph. And then we saw that the algorithm gets stuck. And this is a guaranteed statement that is always true. So it's an if and only if. It's a characterization of caudality. The theorem states only one direction, which is important for the generation task, but it is actually a if and only if. And now let me also talk briefly about running times. The way that the algorithm was stated in this greedy way was, of course, completely inefficient because it had this aspect of do some tree rotation so that you get some unvisited new elimination tree, which means that you basically have to store all the previously visited guys just to know what is a new tree. And this is, of course, very, very inefficient. So you don't want to implement it in this way. But it turns out that you can make the algorithm memoryless. So you can state it in such a way that you don't need to look at all the history. You can just locally, by looking at the current tree, know what is a tree rotation that will give me a new one without storing the history. So this algorithm can be made memoryless and can be implemented efficiently by introducing some additional data structures. And then the running time that we get for caudal graphs in general is m plus n, where m and n are the number of edges and vertices of the caudal graph. So this is the time from outputting one new elimination tree. Yeah, so this is not loopless. This is not constant. This is not the best we can hope for, but it's at least polynomial. We can make it a loopless algorithm in the special case that the underlying graph G is a tree. So this is, for instance, covers in particular if G is a path. Yeah, so then you get a loopless algorithm. Or if G is a star, then you also get a loopless algorithm. We also implemented these algorithms and we made them available on the combinatorial object server. So I encourage you to have a look on this link later. What you can do is you can specify your favorite caudal input graph, and then the algorithm will give you all the elimination trees by tree rotation generated by this algorithm. And now one additional remark, where does this m plus n come from? This m plus n comes from the time that it takes to do a graph search, a single graph search, yeah, by just a classical BFS or DFS. This is what determines this running time. And somehow in the tree case, we can dispense with this graph search and do it somehow differently, and then we improve it to loopless. And another remark, so this graph search is needed to know or to determine which subtrees change their parent in this tree rotation operation. So in this tree rotation operations, I mentioned that some subtrees change their parent, and precisely this thing can be figured out by doing one graph search. So this is what gives this bottleneck, this m plus n. Now, let me also talk about Hamilton's cycle. So the result so far that I presented so far gave you a Hamilton path on the graph associahedron if G is causal. You start at some vertex, you run the algorithm, it terminates at some vertex, and if G is causal, you have the guarantee that you've seen everything. What we want to understand now are cases where somehow the algorithm is very, very lucky and ends at a vertex that is a neighbor of the first vertex. That seems like a very coincidental, highly coincidental case, yeah, a very unlikely case. But actually, it happens in interesting cases. So we use the same algorithm, and we want to add some extra conditions on G that not only guarantee that we get a path, but that we actually happen to get a cycle by the same algorithm. And this extra condition that we need is two-connectedness. So if G is causal and in perfect elimination order, we know that we get a path. And if in addition we require that it's two-connected, then we get an extra guarantee that this path is actually a cycle. So the last guy is actually a neighbor of the first guy. Just a single tree rotation brings you back to the first guy. This is a positive result. There is a negative result. If the graph G is a tree, then this gray code is never a cycle. So this is a negative result. So for paths and stars, you never get a cycle, at least not from this algorithm. We know that there is a cycle, but the algorithm doesn't give you one. Now I just want to mention two numbers to give you a bit of feeling for maybe how powerful or maybe not powerful this result is. So the number of all n vertex graphs is somehow of this order of magnitude, 2 to the n squared over 2, with some hidden terms here. Causal graphs, they are somehow in this order of magnitude. Yeah? So it's substantially less, but it's still a substantial amount of graphs to which this result apply. And if you're interested in two connected causal graphs, and this is the same number, however, with different hidden terms here. Yeah, so now I leave it up to you if you think that this is a strong result or a weak result. Of course, it's weak in the sense that it doesn't cover everything, but it's maybe strong in the sense that it still covers some interesting cases. So let me spend very few words on some of our high-level ideas how to prove this. So one of the key ideas is somehow to relate these elimination trees to permutations. And I already told you in the beginning somehow how we do this. Namely, each elimination tree has a set of linear extensions. If I turn it upside down. And the set of linear extensions, these are all the elimination orderings that correspond to, that give rise to this particular tree. So each tree gives a set of permutations, a set of elimination orderings. What we do now, this is like the one of the steps in the proof. So we have elimination trees, they correspond to sets of permutations. And what we do is we specify a rule how to pick from each set of permutations one representative. In this case, it's the first one from this set of 4 permutations. So that those representatives that we picked, this is now a subset of permutations that we picked, so that the subset of permutations of length n forms a so-called zigzag language. So this is a technical term that was introduced in one of our earlier papers, where we gave sufficient conditions under which a set of permutations can be generated by such a greedy algorithm. And in this way, we translate our problem of elimination trees to a problem of permutations. And then we apply this framework that we developed in this earlier paper, and just basically translate all those notions from this paper to the elimination tree setting. And in this way, you also get this algorithm. So in this permutation paper, this algorithm is phrased in terms of permutations. And if you translate it to elimination trees, you get this algorithm that I showed you. And one of the key insights somehow in this process, which also explains why our algorithm only works for causal graph and doesn't work if G is not causal, is the following somehow neat characterization of causality. So it has nothing to do with our algorithm, it's only a property of causal graphs, namely that a graph G a causal graph G is in perfect elimination ordering if and only if in every elimination forest, every vertex has at most one child that is smaller than itself. Every vertex G, if you look at the children, there's only one, at most one child that is smaller than J. This has the consequence that that there's never an ambiguity for this J down operation. So if I say J down, and I know that G is causal, then there's never this ambiguity that there's multiple smaller children. There's always at most one, and then I always know what rotation to do, and then the algorithm never stops prematurely. So this is somehow the meta reason why it works for causal graphs. And conversely, if G is not causal, well, because this is an if and only if, so if G is not causal, then there is an elimination tree which has a guy which has two smaller neighbors, and then we can prove the algorithm will encounter this step and will run into this ambiguous situation and will stop prematurely. So this is somehow what is going on behind. Okay, that's all I wanted to say about the proofs. Let me conclude with some open questions. So one interesting question is, of course, what about non-causal graphs? Yeah, so we know by this Manville-Parillo theorem that there is always a Hamilton cycle. We just don't know how to compute it efficiently for non-causal graphs. Yeah, so our algorithm does it efficiently for causal graphs, but we don't know it to do it efficiently for non-causal graphs. Another interesting direction could be to apply these methods to more general families of polytopes. So I already told you that these graph associators, that they generalize many things like associahedra and permutahedra and hypercubes and whatever. But this is not the tip of, or how to say, this is not the end of the story. There is even much more general families of polytopes. So graph associahedra and hypergraph associahedra and nestohedra. What about this kind of objects? Does our framework still apply in this setting? Yeah? We know of some settings where it does, but we haven't yet fully worked out everything. Also, maybe algorithmic question you could ask about this time bound. Can we make it more efficient? Can we improve this O of m plus n per elimination tree? I told you for trees we can do loopless, but maybe this can be improved in general, or maybe by imposing some extra conditions on G. So I think this could be an interesting direction. That's all I wanted to say. Thank you for your attention. And now I look forward to your questions.